in anti-chronological order. So quite a bit of this work was done before we started to work on the embedding of Rust into Coq. But then we thought that there's actually the whole tool chain we have with Hex is actually probably a nicer way of doing it. So that's why there are two talks. So this is a bit about formal security analysis of a blockchain voting protocol, and this is a fairly small, or this is an election that works for smaller groups because you need to do everything on chain. We're working with an industrial application of actually putting this in practice, and a protocol like this one will be used to hold elections on the Concordian blockchain. So there will actually be a lot of money involved. Because if you can rig the elections, then you can actually take over the foundation, so you can get quite a bit of influence. So this is also what Lasse just had on his slide. So there's the new Data Protection Act. So it says we should have a very high degree of robustness to avoid functional errors and to withstand manipulation. The law never says precisely how we should get these guarantees, but by pushing the technology, we can actually influence the interpretation of the law. So if it's actually feasible to develop these things completely formally, then if you would carry this out, you have such a thing on chain, and it would break, then the onus is on you to actually show that you actually did your work well. So that's one of the reasons why we're doing this. We want to show, well, this is currently possible with, well, fairly limited resources. There's a lot of money sailing on these contracts. So if we invest a moderate amount of that on security, then actually we can get something that has a very high level of security. And there's what you can see here at the bottom. There are more and more experiments with electronic voting, and there are many challenges with that. So they're common in Estonia, they're common in Brazil, they're common in India. There's new regulation in, I believe, Germany, where they're also experimenting with it, and then there are caps on saying that only, so often it's for mail-in elections. I think the current Swiss regulation says it can only be used up to 1/3 of the population. So there are more and more experiments with it, but it's people are still careful with it, and for very good reasons. And this is part of an Innovation Foundation project to actually make these voting protocols much more secure, and also really looking at electronic voting. So there's a tight connection between voting and blockchains. So we see voting in the screen here is very small. So we see voting used in blockchains. So actually the consensus already uses a voting mechanism. We have the governments, where you can see who gets to control the chain, or who gets to control a smart contract. We have these decentralized organizations, and most people will recall that on Ethereum there was a large amount of money on such a decentralized organization, and due to a re-entrancy bug, people could steal a lot of money from these projects. So already in this voting, we know that it's a very tricky situation, and it makes very good sense to use a bit of formal methods in this space. On the other hand, and that's the focus of the talk today, you can use blockchains. So any voting needs some kind of bulletin board to publish the results, and you want to publish the results in such a way that people can actually check by themselves, my vote has been counted in the right way. And that such a bulletin board could very well be a blockchain. So that's how we're using it here. And the nice thing about a blockchain is you cannot change it, and it will always be available. So there's a lot of duplication. So specifically, what we're looking here at is what are called boardroom votes. So well, you think in a lecture room like here, and that's sort of the size what one can do in these votes. So also the lots of things about manipulation of who votes and so on, coercions, they're not so urgent as they would be for national elections. So the setting here is a bit different. So there's this open vote network which has been launched on Ethereum. It has been running for a while, and people use it, and you can use it quite pleasantly for small elections. A bit about the setup. So you use a group that has a hard Diffie-Hellman problem. I think most people have seen this. And you have 2 rounds. In the first round, the public keys are put on the chain and they're verified, and then the reconstruction keys are computed. And these keys are computed off-chain. And in the second round, the ballots are computed using the reconstruction key, and we have a zero knowledge proof that this ballot actually is a valid vote. So it's either 0 or 1. And then finally you put those on chain, and then anyone can check that their vote has been counted correctly, and anyone can check what was the result of the vote. So how many people voted in favor of Coq over Lean, say. So these are the formal properties. So self-tallying. So everyone can check that their ballot was counted correctly. Everyone can compute the result without any external help. We have maximal ballot secrecy. So each ballot can be, so we have this in CPA. So that's a well-known property in security. So it's indistinguishable from a random number. And then finally, the result is publicly verifiable. So anyone can check that the whole election was actually carried out in the right way. So now what do we want to prove about this smart contract, about the voting contract? So one is, so was it cryptographically secure? And the other one, was it implemented correctly? Already the paper about the open vote protocol, it contains an analysis why this protocol was secure. We checked it carefully, and it's almost complete, but there's some steps missing, and that often happens if you write a proof on paper. So there is a cryptographic proof, but there were some, we needed to work on a bit on it to have a complete proof. And then we want to verify that proof of that protocol. And then of course on top of that, so the paper about the Ethereum implementation, or even the first paper that was not connected to a blockchain. There was nothing about the implementation, or nothing proved about the implementation. So the first thing what one would want to do is prove things about solidity. As far as I know, there's, say, no Coq library that allows you to do substantial proofs about solidity, and I'm not aware of any other tools either. There's some more lightweight tools to check some things about solidity. But there's certainly no interactive framework. So the first thing we did was to re-implement this in Coq, and for this we used our Concert framework. So Concert, it models an abstract account-based blockchain. So there are 2 models of blockchains. One is using accounts, so that's what Ethereum is using. The other one is using UTXO, so you keep track of the unspent transactions. So that's Bitcoin and a number of others. But we stick to this particular model, and then we have pure smart contracts. And as Lasse mentioned, there are quite a few blockchains that are using pure smart contracts. So that's a good motivation that this can actually be done. And there's you can write many of the smart contracts you would like to write in that style. Of course, it's pure programs that manipulate state, because you're always interacting with the blockchain. So there's one big state that you're updating. What we're doing, and this is something that Mathieu also touched on in his presentation about what's going on in Coq. So Concert is part of this big ecosystem that we're building collaboratively, where we have the meta-CoQ, certi-CoQ, verified extraction, and so on. So this is part of this. So we do extraction from CoQ to Lambda box. So that's basically formalizing in meta-CoQ the extraction that was in the paper by in the thesis by CoqPL'24. And then we have a small printing layer. I have a picture on the next slide. A small printing layer to Rust and to LEGO. So Rust is what's used by Concordium, and then you want to do also a bit of glue code to actually connect to the blockchain, and the same for LEGO. Another thing we've done was to add quick check testing, so you can test temporal properties, you can test functional properties, and what we did was to implement quite a few of these paradigmatic contracts, like a DAO, decentralized exchange, an escrow, an ICO, and then we looked around at some of the big hacks. So everyone knows what was wrong with the DAO. There were the reentrancy issues. For the DEX, there were a number of attacks on these things, and basically what you do is you write down the property that if you exchange coins, then the total number of coins should stay the same. And what we did was use quick check to actually generate traces, and then you can actually find these attacks there. And so we could actually reconstruct these 0 days. So if you would actually have, well, while you were implementing them, write down the invariants, you would have prevented these attacks. So here's a picture of what this thing looks like. So this is now part of the whole verified extraction certi-CoQ pipeline, the optimizations that we added there. And so what we can do here at the end is from a Lambda box to a small printing layer. So a big part of this is actually verified in CoQ. So what we did was to actually implement this open vote network in CoQ, and then prove that it's correct. And that gives us the first property that we want. So OVN is actually self-telling. So that's just a functional property. And what I should mention, this is actually an industrial application of CoQ. So this was supported by 2 different blockchains. So we both support the Concordium blockchain, which does Rust, and the Tezos blockchain, which does LEGO. Now there are two more properties that we want to check. So there's this maximum ballot secrecy and the distribute freeness. Now just a refresh on how you do cryptographic proofs. So there's this provable cryptographic security. So you have a mathematical argument reducing. So if I can attack this protocol, then I can also break this really hard mathematical assumption. And that could be something like prime factorization, or here the Diffie-Hellman assumption. And this is called game hopping, because you're reducing one protocol to something similar. What we need there is a computational framework that captures probabilistic and stateful algorithms. So that's what we have in the SS proof system. That's together with Theo and Lasse and many others. So one observation, and that's something that people have started to appreciate, for example, in the Avers project, is that the game hopping usually is not very modular. It's been directly also observed by, in the book Joy of Cryptography, that actually writes a bachelor level textbook on cryptography, where they actually found the same style. What you do there is you take code blocks and you manipulate them quite nicely, and I think that this can probably be extended a bit further in programming logics. But this is something that cryptographers quite enjoy. Before SS proof, this didn't have a formal semantic. So what we did in SS proof was we took this picture calculus and we actually put it on top of a program logic. So this is a library in CoQ for the state separating proofs, and it's based on the Dijkstra monads framework that was developed also to get the semantics for things like what one does in F-star. And we look at the monads for state and probability, and these can be combined in a modular way. Yeah, that's what I said. So the program logic is a probabilistic relational OR logic. And you've probably seen this in EasyCrypt Proof Assistant. So what do we prove? When did I start, by the way? Because okay, that's great. So what we do is we have there's this general notion of zero knowledge protocols called Sigma protocols. So that's the class of zero knowledge protocols that we're looking at. And then there's a number of constructions. So if you can prove certain properties in zero knowledge, you can combine them with what are called the AND and the OR construction. So you can prove two things that one of two things hold. And we did these constructions, both the basic properties of Sigma protocols that it is a zero knowledge proof, and also these OR and AND constructions. So the OR construction is what we need here. And then we also did the Fiat-Shamir transform. And this is typically something that's very hard to do correctly, and that's where there were some real world attacks also. So that's good that we're actually verifying these things. And so what we have in concerts is an actual model of the execution, the scheduler of the blockchain. What we have in SS Proof is we also need to model the blockchain state in some way. And what we did here was to take an ideal functionality in the sense that cryptographers do it together with a scheduler. And then we prove in SS Proof that the OVN has maximum ballot security and is dispute free. So those were the two properties that we still wanted to prove. And then, yeah, as I showed you before, what we can do here is actually extract to all these languages, to Cameligo and to Rust. There's a bit of overhead in Rust because you're going from a functional language, Lambda box, to Rust. So you don't get idiomatic Rust code. It's also a bit slower than you would want, and especially if you're running on a blockchain, you want to be careful there. So there's an alternative that we can do, and that's what Lasse presented. So instead of extracting from Coq, we can embed code into Coq. And that's what we've been doing with this whole Hex framework, which is a framework that we're collaborating across provers. So it's also being used by people in FStar, in ProVerif, in EasyCrypt. So we have a joint language and a big joint pipeline. And what Les also pointed out is there's an automatic proof of that the imperative code actually refines the functional code that we generate. So we have, instead of what we first did by hand, was we proved those two programs to be equivalent by hand. Now we just write the Rust code once, and we have this translation into the two libraries. I should also notice that both these libraries, they're very, very big. I mean, Concert uses both QuickCheck, it uses quite a lot of metacoq, so it drags in a lot of dependencies. On the other hand, SS Proof also, I mean, has a lot of dependencies. That's based on MathComp. So actually automatically proving that one refines the other, that there's quite a bit of infrastructure that goes into that. So to connect with the first presentation we had this morning, we're now going from either Coq to Rust or from Rust to Coq, but still we're trusting the Rust compiler. What would of course be nice, I mean, in the end what we have running on chain is WebAssembly. So if we can go efficiently directly from Coq to WebAssembly, that would be even better. So yeah, that's what I tried to show you. So we have the first smart contracts that was both proved functionally correct and cryptographically secure, and we have very general libraries that can be used to prove these things. And we're building a whole infrastructure using Hex and using these big libraries. And both of these can be done by either extracting or by embedding from Hex. Now, just want to pitch a project that we're actually working on. So there's a project by the Innovation Foundation. And what we're going to do is to collaborate with the Microsoft. So Microsoft has a team building the election guard. So election guard is actually used a lot in practice. So it's been used in the Republican primaries, for example, and it can not only be used in electronic elections, but also in physical elections. So this is a very real product. So what had been done before was that the crypto that was in there was replaced by Hackle, so that they actually have formally verified cryptographic code already in there. So that was version 1. What we now want to do is replace that by our libcrux library, which is a library we're developing together with Crispin, which actually brings all verified crypto together in one joint Rust library. And then what we've shown in this project is we can do these zero knowledge proofs that go into the OVN, and those should scale to election guard. Doing that is still a big project, but it's the direction we want to go in. But that's what I wanted to tell you. Thank you. It's been a long week.
So actually, I did have one question. So do you have a sense for if you could only prioritize one, whether there are more bugs in the implementation or in these high-level protocols, thinking about security bugs?
We know that almost all the bugs are memory safety bugs. I think that's...
I mean in contracts, right? So
in contracts. I don't think we've seen enough.
Okay.
Well, chain analysis has very nice overview of attacks on smart contracts or attacks on blockchain projects in general. Also see how they're abused by criminals and by nation states and so on. They have a breakdown. So part is it the economic incentives, which is out of scope of this work. And in part, that's a field of cryptography that's still being developed, so rational cryptography. There are quite a few that are functional correctness bugs that could be implementation of rational numbers, but also off by one errors. What I mentioned, something started moving here. The other one, the Fiat Shamir that I mentioned, that's come up here, that has been a real issue in zero knowledge implementations, and that's very acute because they had a bug in Zcash, for example, where there was basically an off by one error. There was a very nicely published paper, and they had used a different convention in the indices, and this was faithfully implemented by the software engineers. This would allow you to print as much money as you want, and it would be completely untraceable. So those bugs in cryptography. So this was a functional correctness bug, but the related Fiat Shamir is also something that's very dramatic. So in both, we have very real examples in both problems in functional correctness and in cryptographic security.
Thanks for the talk. You briefly mentioned the CoqPL'24 certified compiler. How does that compare to the current setup with Concert, and would there be any drawbacks compared to your current setup if you were to change to that compiler?
Not a lot, I think, because so. Yeah, what I show here. So basically, what we do here. So we optimize in the box, and then from there on we use the same pipeline. So this has now been integrated in verified extraction and in Sidorenco. I mean, that's the integrate part has been done meanwhile. So then we just continue this line and end up in WebAssembly here. What we don't have, I think, is what we should probably do is some kind of foreign function interface, which is something we've been discussing, because you need to do the interaction with. So now we have glue code to get the interaction with the blockchain, and we would need something similar at the WebAssembly level. But in general, I don't see an obstacle using that line of attack. Whether that's fast enough, I think that could be fast enough. That there's a big question of whether you want to have a garbage collector on chain. I've been talking to some of the engineers, and they said, well, even if people add a garbage collector to WebAssembly, we probably don't want to have it on chain because it's too unpredictable. But otherwise, I don't see obstacles, but it's also not something that we've pursued very actively. But I think it's a very interesting direction. Thanks.
Okay, let's thank Bas.